This is an example problem where we are asked to find the electric displacement field, D, along with the electric field and polarization everywhere, and then find the bound charges on the dielectric. What I've drawn here and what I want us to consider is that if I have kind of a thick outer tube of dielectric material, I don't know, PVC or rubber or something, with a air gap or vacuum gap between there, and then a conductor on the interior. I want to think about, because we only care about free charge here, right? I want to think about then going and putting a positive capital Q charge onto the conductor. And then this positive capital Q is all of the free charge that we have in the system. And so we are going to then use the macroscopic Maxwell's equation to find the displacement field everywhere. So the macroscopic Maxwell's equation is del dot D is equal to rho free. For us, we don't so much care about that. We want to get the fundamental theorem when applied to this, which is going to be the surface integral d2x n hat dot d. And so this is the fundamental theorem. If I did a volume integral of both sides, I'm going to find that I need to, the volume integral of a divergence is the surface integral of a flux. And so that's this side. And then I'm simply going to get the volume integral d3x times rho free on this side. We have to draw or figure out what our Gaussian surface is going to be for this case. We should already know we have a cylindrically symmetric case, so we want to draw a Gaussian cylinder. So the Gaussian cylinder, right, is going to look something like that. It's going to go down with a finite length, and so we would call the length of the Gaussian cylinder L, and the radius of the Gaussian cylinder we might term S. So taking this as our surface, we're going to use symmetry of the problem, and that symmetry is going to say that the normal vector, because I have to go through all surfaces, the normal vector on the top and bottom, this n hat will be in the minus z hat direction, this n hat will be in the plus z hat direction, and the n hat on the edge here, this n hat will be in the s hat direction. And due to symmetry, right, due to symmetry, we know that the displacement field needs to be only in the s hat direction, and furthermore it can only depend upon s. I can rotate this thing and I can't tell any difference, so it can't depend upon the azimuthal angle phi. Also, I should be able to move it up and down, so it can't depend upon the total angle. So here's my Gaussian surface in this picture, and so again this distance here is s here. Because of that symmetry, the n hat dot d on the top and bottom is of course 0, so I'm simply going to have the flux through the side, and so I need the surface area of the side, which is simply its circumference times the length, and so this is going to be 2 pi s times L, and then times ds as a function of s. On this side, we have piecewise 0 if s is less than, let's call the inner radius a. So let's call this guy a. I'm going to call the radius to the inside surface b, and call the radius here to this outside surface c. Okay. So anyways, here we're going to have that, and and on this other side we're going to have the charge per unit length times the length. Oink, right? So, and this is for s greater than a. And the reason this happens, right, is when you put free charge on a conductor, it all goes to the surface. So we're only going to have charge on the surface. we're not going to have any charge in the interior of the conductor, and that's just one of the features of a conductor. And so that's why we have 0 here. The integral, if I'm inside the conductor, is going to be 0 because there's no free charges in the interior of a conductor. At this point, we are basically done with D, and so we can find D everywhere. D as a function of R, I guess, would be written now as 0 for s less than a, and it would be written as q over L divided by 2 pi s hat for s greater than a. And that's it. Now to find E everywhere, we have to remember what it's called. I think the I don't even remember what it's called. We have to remember this formula, that epsilon naught times the dielectric constant, or the relative permittivity, epsilon r, times E is equal to D. Well, for us, what's interesting is the only case where epsilon r is different from 1 is when S is between B and C, right? In this region here, epsilon r is different from 1. And so I can go ahead and explicitly write that, right? Epsilon r as a function of S is going to be equal to 1 for S less than B, to some epsilon r non-zero for B less than S less than C, and 1 for S greater than C. Okay. And that's just saying that the dielectric only exists in this region. Simply taking this and plugging it in here, we will into this formula, of course, will tell us what E is everywhere. So E everywhere is going to be, now we have 4 different regions, right? We're going to have region 1, region 2, region 3, and region 4. And so I need a big option here. We're going to 0 for S less than A, which is region 1. And then we're going to get Q over L over 4 pi epsilon naught times 1 over S hat for A less than S less than B. Then we're going to get Q over L over 4 pi epsilon naught 1 over epsilon R 1 over S hat for B less than S less than C, and then Q over L over 4 pi epsilon naught 1 over S hat for C less than S. That's region 2, that's region 3, and that's region 4. To find the polarization everywhere, we're going to use the the other equation that we haven't written down here that also relates to D and E, and that is D is epsilon naught E plus the polarization. And so that means simply that the polarization is D minus epsilon naught E. Well, we can go through this really quick, and we can see that in regions 1, it's 0 and 0, so that's going to cancel. In region 2, when I multiply by epsilon naught, I'm going to cancel 2. I have Q over L over 4 pi 1 over S hat. Q over L over 4 pi 1 over S hat. So in regions 1 and 2, I'm going to get 0. These two are going to exactly cancel. Same in region 4, but in region 3 I'm not going to get 0, so just go ahead and write out what I have. And so P is going to be 0 for S less than B, which are regions 1 and 2. And then we're going to get Q over L over 4 pi 1 over S, I guess, 1 over S. And then I'm going to get 1 minus 1 over epsilon R S hat. And this is for B less than S less than C, so this is in region 3. And then I'm going to get 0 again for C less than S, which is region 4. And should be no surprise for us, right? The polarization only exists in the region where we have a dielectric. So that's kind of interesting. We got that. Now the last thing that we want to do, right, for this problem is find the what the surface charge densities on these two surfaces are. And so to do that, I want to look at these surfaces, and I notice that in this surface my n hat is equal to minus s hat, and on the outer surface my n hat is going to be equal to positive s hat. Okay, why did I do that? Because our formula for charge bound charge density on a dielectric is simply n hat dot polarization. I have the polarization, and so on the boundary at B and at C I need to dot this thing with n hat. Okay. I'm going to find, of course, that the sigma B on the inner surface is going to get a minus sign because I have minus s hat dot s hat. It's going to give me a minus sign. So minus Q over L over 4 pi 1 over B, because that's where it's evaluated, 1 minus 1 over epsilon naught. And then sigma sub B on the outer surface is going to be a positive, so I have a positive s hat dot s hat, and so that's a plus Q over L over 4 pi 1 over C, in this case 1 minus 1 over epsilon r. And that is it. So now I have the displacement vector everywhere, the electric displacement vector everywhere. I have the electric field everywhere. I have the polarization field everywhere. And I have my surface charges, the bound charges on my dielectric. And that's how you do problems where you're asked to find, or where it's useful to work in the displacement field.